In our last class, we talked about what a proportional relationship was, and we were looking at tables. And what we're going to do today is just transition into what this looks like graphically, because there's different representations that we want you to know. One is a table, the second one's a graph, and then we'll look at equations next. So when you're looking at the graph of a proportional relationship, now first of all, well, just a little bit of review over graphing. I've got two variables here, the hours worked and the money that I'm earned. So I'm going to use your knowledge that you've gained in science, hopefully. Which one of these, hours worked or money earned, is the dependent variable? All right, well, if you were paying attention in your science class or maybe in your math class last year, you would have gotten that right. That the dependent variable is the money earned, because how much money you earn depends on how much you work. And so that's, and when we put it in a table, this isn't always the case, but usually we put that dependent variable in the second column. And if I'm thinking about this in terms of x and y, normally the dependent variable is usually our y variable, and the independent variable is our x variable. You don't have to use those variables, but those are the most common ones in mathematics. So if I want to graph that relationship, which axis, so the axes are these two lines, right? So I have my vertical axis, let me just put vertical axis right here, and I've got my horizontal axis. So of those two axes, axes being the plural of axis, so of these two axes, where does the dependent variable go? All right, the correct answer was on the vertical axis, okay? Which means that my independent variable is going to go on the horizontal axis. And remember, normally the independent variable is my x and the dependent variable is my y. And when I'm just looking when I'm graphing in mathematics, that x is usually, or is going to be the horizontal axis, and the y is going to be the vertical axis. And that's where the independent and dependent variables go. But in this problem, I'm not going to label this x and y. I'm going to label it with the variables I'm actually using. So I'm just going to put in there the money and the hours worked. Okay, so now I'm going to go and graph each of these points. Now, to graph them, I need to give this some sort of a scale. Okay, so I have to put numbers on my axes. So you notice here for the hours worked, it goes up to 10. So I'm just going to put 10 little lines. So 1, 2, 3, 6, 7. This doesn't need to be perfect, you know, you want to roughly space them out. Now, on the vertical axis, it's going up to 150, so I'm not going to want to put a tick mark for every one. Let's go ahead and put a tick mark that represents 10. So this would be like 10, 20, 30, 40, 50, and I'm not going to put every number. 60, 70, 80, 90, 100, and then 10, 20, 30, 40, 50. Okay, so I'm just going to go up by 50s. And that's not totally perfect, but close enough. Now I'm going to graph each of these points. So 115 is going to be roughly right here. 230 is going to be about right here. 150 is going to be up here somewhere. And 1.52250, again, we can only be so accurate, but it's going to be right about there in the middle. Now, if you did this, now my graph's going to be a tiny bit off, because if you notice like those first couple spaces where I made a little bit too big compared to the rest of them. But if you do this correctly, here, let me make my line thicker so it looks like my points are okay. When you draw your connect the dots, what should happen is they should all be in a straight line, and it should start at the origin. The origin is 0, 0, so it should look like this. Now, you notice I put a big, fat, thick line to try to go through all those points. You know, if I graph paper and I put them on there exactly, then all of those points would be exactly on this line. Again, I'll just make big points to kind of cover up my mistake. So that's what the graph would look like for this. Really important, you put your scale on there, and you should get them all lined up. All right? So let's take a second and look at this one. Now, I'm going to ask you to go backwards. So I've given you the graph. I've given you 1 point on the graph. And what I want you to do is go in and try to fill in 4 values in that table based on the information on the graph. All right? Now, the answer to this is not, I mean, we're all going to get different answers because I didn't tell you what values to put in there. One that I'm assuming everyone would have picked would have been 880 because that's the one that's given to you. So the 8 is the hours worked, and I could just kind of take that down to my horizontal axis. There's the 8, and then the 80 is taking that over to my vertical axis. All right, so that's one point. Now remember, if it's a proportional relationship, I can just scale that ratio to get new ratios. So let's say one that's always nice is to work with ones. So let's take this, and I'm going to turn that to a 1. Well, I could scale that down by dividing by 8. So then I got to do the same thing over here. So 110 would be another point on that graph. So based on this, let's put some scale. 1, 2, 3, 4, 6, 7, 8. So 1, 8 is going to, and I'm just going to go right to the line because it's going to have to fall on the line. So this would be, looks like, that's going to be about 10. Let's see, 20, 30, 40, 50, 67. Oh, it matches up with the lines on my table. Didn't even try to do that. So 110, and then I could scale it up to get some other ones. I could multiply it by, I don't know, 3. Do that on both sides. That's going to give me 330. So on my graph, that's going to be like right there. It's probably a good idea for me to label my points. 110, 330. And then the last one, let's go ahead and double the 330. Whoops. So double that, times 2, times 2. Gives me 6 and 60. So that's going to be 3, 4, 5, 6, 60. It's going to be right there. All right, so and again, the values that you come up with could very well be different. One that's nice to use, like I said, is this one right here, okay? And this does have a special name, okay? This is called the unit rate, okay? Whenever you see that like unit rate, unit in mathematics means 1. So, and you can tell on this one, it's saying if you work for 1 hour, then you're going to earn $10. And so that unit rate on the graph always appears right here. When my independent variable, which is the hours worked, is 1, and the dependent variable, the money earned, is going to be whatever it is. In this case, it's 10. So the unit rate in this problem is going to be $10 per hour, which, if you remember, connects back to our last unit. So our last unit we talked about, or our last lesson, it talked about, what do we call this number when you multiply? In this case, we're multiplying all these by 10. What is that number in a proportional relationship called? All right, if you said constant of proportionality, good job. All right, so what does it look like when it's not a proportional relationship? Well, this was the one from last class that wasn't a proportional relationship. And so if I went through and graphed this, let's give it scale 1, 2, 3, and 4. And then we're going by 5. So 5, 10, 15, 20, 25, 30, 35, 40. I'll just put the first couple of numbers. Well, actually, I better get up to at least 25, right? So 125 is going to be right here. 230 is going to be right here. 335 is going to be right here. And 440 is going to be right here. So here's kind of what that relationship would look like. They're still all in a straight line. When you have something that's in a straight line, we say that there's a constant rate of change. Okay, so this has a constant rate of change, just like my other proportional relationships. But if you compare them, okay, so the lines in blue are the proportional relationships that I've done so far, and that one in red is the one that we just graphed. I took the scale off, but when you look at those, what do you notice about those relationships? Like what does the proportional and not proportional relationships have in common? And what's different about them? All right, you might have said some different things. Some of the things that I noticed, like looking at this, things that are in common, okay, well, they're all straight lines, okay, so, which is, that means that there's a constant rate of change. You might also say that they're all going up or that they're all increasing. Something, along those lines, that like each of those, the money is increasing the more hours that you worked. And I don't know, you might have come up with some other things. The main difference in these is kind of where they're starting, okay, if you're looking at it graphically. The proportional relationships start at the origin, okay? Let's say start at origin. And the not proportional relationship doesn't. So when you're looking at them graphically, that's probably the most significant difference between those two. All right, so the last problem here, I'm just going to have you go through and answer a few questions about this relationship. So this is comparing how much you would weigh on Earth versus how much you would weigh on the moon, which is a proportional relationship. Oh, I just answered that question for you. Yeah, this is a proportional relationship. Okay, the second one. Based on the graph, how the graph is drawn, which is the independent variable? All right. So the reason that the independent variable is the Earth weight is because it's on the horizontal axis. So remember, that's usually where that's where we're going to put the independent variable, which means the dependent variable is going to be the moon weight. And for this particular problem, I could have set up the other way. I could have made the moon weight the independent variable, but how we wrote it here, the Earth weight would be the independent variable. Okay, so if a person weighed 40 kilograms on Earth, how much would they weigh on the moon? When you go through, and there's several ways that you could have solved this problem. Now, one way I'm going to show one method for doing this, and in the last problem, I'm going to ask you to try to use this method, and it's something we're going to be working on more throughout the unit. But it's setting up and solving a proportion. This is something that might be a little bit new, not in terms of how you get the answer, but how you organize your work. This might be kind of a new skill for some of you. So it might be a good idea to jot this down somewhere in your notes, because we're going to be coming back to it. So to set up and solve a proportion, I'm going to start by labeling my ratio. And so labeling the ratio, we're just talking about the two variables that I'm comparing. And so I'm going to go ahead and put the moon, I'll just put moon kgs on the top, and I'm going to put the Earth kgs on the bottom. I could have flipped those around the other way, but that's how I'm going to set it up. So that's the first thing, is labeling what the two variables are. And when I do this, I'm going to set it up using fractions. The second thing is I'm going to write down the information that's given to me. Okay, so in this problem, what's given to you is that if you weigh 100 kilograms on Earth, 100 kilograms on Earth, I'm going to weigh 16 kilograms on the moon. And I got that from the point that's provided on the graph. So that's the information that's given. The third thing in setting up a proportion is putting a ratio about what you're trying to find. So what am I trying to find in this problem? I'm trying to find how much would they weigh on the moon. So in my ratio, the way I wrote this, I might put the moon weight on the top. So I'm just going to make that X. And then I'm going to make the Earth weight, well, what do we say on this one? The question was if it was 40 kilograms. So that's what it looks like when you set up and solve a proportion. You label the ratios, you write what's given, and then you're trying to find it. So how do you solve one of those? Well, and again, this is kind of like a rate table. You're just taking out the lines in the table. So you want to think about, well, what do I have to do to go from 100 to 40? Okay, so I'm going to be trying to find the scale factor. I'm going to just call this K. So 100 times what gives me 40? Well, let's just use a little bit of algebra. I'll go over here off to the side. 100 times some number is equal to 40. Well, that's just a one-step equation. Let's divide both sides by 100. So K is going to equal 40 over 100, which I could simplify down to 2/5. So that tells me that if I multiply that ratio by 2/5, Let's get rid of the k now and change it to 2/5. 100 times 2/5 is going to equal to 40. But in order to keep these ratios equal to each other, which anytime you have a proportion, all the ratios are equal, I have to do the same thing on the top. So I'm going to take 16 and multiply it by 2/5 to get that x value. I'll just do that off to the side. So x is going to be 16 times 2/5. Well, that's equal to 32/5. I guess you could leave your answer like that, but really, like, no one says, oh, I weigh 32/5 kilograms. So I'd probably write it as a mixed fraction, 6 2/5. Or even better is probably writing it as a decimal, okay, because that makes more sense when you're talking about weight. So the correct answer is that the person would weigh 6.4 kilograms on the moon. And you probably got that answer using a different method, which is totally fine. But in the last problem, I'm going to ask you to do this, to try to, in your own work, to set up and solve a proportion. Okay, so that's what it should look like. All right, so in this last question, I want you to set up and solve a proportion to find out how many kilograms on the moon is equal to 1 kilogram on Earth. Okay, so for this one, I'm going to start with labeling. The moon, I'm going to put the moon weight on the top and the Earth weight on the bottom. The reason I'm putting the Earth weight on the bottom is because you want to try to figure out the 1 kilogram on Earth. When we're working with like ones or units, it's usually nice to have those on the bottom. If you did it the other way around, it's fine, okay? But that's probably where I would have set up. So here's my given information. 100 kilograms on Earth is 16 kilograms on the moon. What am I trying to find? Well, if it's 1 kilogram on Earth, what is it on the moon? So this one, finding that scale factor is pretty easy. How do I go from 100 to 1? I could just write divided by 100, but I'm going to write times 1 over 100. Okay? When I'm talking about scale factors, it's always, in math, we say the scale factors is what you're trying to multiply to go from the first ratio to the second one. That's going to become a little bit more important later on. If you wrote divided by 100, no big deal. You're just scaling your ratio down. But if I ask what's the scale factor, it's what do you multiply. So if I take 16 times 1 over 100, okay, or divided by 100, that's just going to move the decimal 2 places. Okay? So let me just do this off to the side. 16 times 1 over 100 is just going to equal 0.16. And so I would say the moon weight is 0.16 kilograms per 1 kilogram on Earth. All right, so that is it, and good luck on your assignment.